Another episode of Wonderful People. Hello to the Simuleos internet of welcome back, so says T.S. Jost. I hope you guys are all having a great day. I was trying, I promise, yesterday at the end of stream, I said I wanted to start streaming at 3 o'clock p.m. my time. I was unable to do that because of a lot of drama, not only with just a lot of drama. There was just a lot of drama. I'm not going to go into it. I need to stop talking about drama on stream. Point is, lots of stuff happened. I was not able to get as far as I wanted to with anything. So today we're coming back live, and we are going to be coding up a quilt. That is what we're doing today. TS Joss is fine. Love you anyway. Oh, I appreciate that. Thank you. Okay, so let's go ahead and open up Zernal PP. Talk about what we mean when we say that we're coding up a quilt, and go from there. All right, there we go. Oh man, today's gonna be a day. Okay, so what are we talking about? I'm creating a project called Quiltify.jl. The JL means that it's in Julia, so I can just erase that because it's not important for this information, for this conversation. The point is we're taking some image, any image we want. So let's say again, it's just going to be, I don't know, it's going to be some guy. Okay, some robot. Here's the robot. It's going to have little robot. I should show tomate. It's going to have robot eyes, little robot mouth, robot buttons, maybe, robot shirt, whatever robots have. I don't really know what robots look like. But the point is we take some sort of image. It doesn't matter what the image is, and we turn it into something that we can represent on a quilt. Now, what exactly is a quilt? Some people ask that question. It's what you think it is. It's a blanket, like the blanket that your grandmother would make for you, that is basically composed of a bunch of squares, which could be considered to be pixels. But these squares can be split up into triangles. So in principle, they have quarter squares, not just full squares that you can use. So in the quilt version, it would actually probably look identical to the other version here. So we'll just say quilt robot. All right. So what does this entail? Well, first of all, we have to do some sort of color quantization, just to see what colors are relevant in the original image and what colors we need in our quilt, right? So that will say what colors we need in the quilt. After that, we have to do something that I'm calling Quixelate, which is basically turning the image into quilt pixels, which again are quarter squares or something that you can use. And then finally, after that, we have to apply all the texture. So we're going to do apply texture. Okay, let's pretend I can write because I cannot. Apply texture. And that's it. That's the whole shtick, the whole shebang. We are on the color quantization step. So when it comes to color quantization, what is that? You might be asking. That's a very good question. Thank you so much for asking that, person who didn't ask that in chat. Color quantization is, again, the art. Quantization is the art of basically figuring out what the, let's say you have an image and you want to select the, what on earth? And you want to select the 8 best colors in the image. Color quantization is basically taking an image, selecting those 8 best colors, and then basically casting every other pixel in the image to be of one of those colors, right? So if you look over here to this image, we basically have this giant rainbow thing. Here, let's go and start with this giant rainbow explosion thing, and we can quantize it so we have 64 colors. And as you can see, like, it looks a bit more pixely. And if we quantize it to 8 colors, now it looks like abstract art. And so this is kind of the idea with color quantization. We start with something that is clearly pretty well defined. We make it, so that there are less colors associated with it, but still the image is identifiable. And that's the whole shtick. That's what we're doing. Now, how does this work? I'm doing a very bad job of describing this, but I'm hoping it's kind of okay. So what we do is we create some sort of color map here, where we could have red on one axis, blue on another axis, and green on an axis maybe coming out of the board over here, right? And so the idea is that every single pixel in our image will have some sort of combination of red, green, and blue. Now again, you could use other color spaces like HSV or whatever. We tried that yesterday and it didn't seem to work okay, but that was just because of Julia, probably not because of the fault of the algorithm. So what we do is we then split this up into halves. So the idea is we split it up along X, and we split it up along Y. So here we have something there, and here we have something there. And then we split it up again, here and there. We split it up again and again. Basically, we just keep splitting it up in halves over and over again until eventually every single particle in the simulation, every single pixel in the image has its own box which represents its specific color. And so that's the idea here. This is a quad tree. In 3D, it's going to be an octree. Oh no, I'm going to have to split that up again, aren't I? Something like this. So the idea here again is that every single box has its own color. And importantly, this big old box here, which has more than one particle in it, here, has some sort of average color that corresponds to all the particles in the box. So the idea is we find all the boxes. Then after finding all the boxes, we find the n most important boxes, where n is the number of colors that we want to quantize. So as of yesterday, we had the ability to do this relatively straightforwardly. Now we are going to have to ask ourselves the question, how exactly do we sort our nodes so that we know how many particles are in each box and all this kind of stuff. So we've got a lot of questions that we have to answer here, and this is kind of where we're hopping into today. So hopefully that was an okay description. It probably wasn't that great. I'm sorry about that. I do have a video on my YouTube channel here. I'm just going to do this for now. In fact, let me get you the actual YouTube video over here. So let's go to youtube.com/user/LAIOS, and let me get you the actual video. Learning, no, shh, and then we can go from there. So most popular, and it will be this one, removing colors, color quantization. To another, shh, stop talking, you're annoying. Okay, so something like, minus the 1 second here should work. So if I load that, hey guys, no, shut up, you're annoying. Okay, so that's the actual video I did earlier on color quantization. Again, actually, if you look at color quantization, in principle, there is a number of different ways to do the quantization step. So if we just Google color quantization, and we go to Wikipedia, basically any way in which we can cluster these particles together will allow for us to do the color quantization. I'm using an octree here, but again, you can use whatever you want. If you want to use k-means, if you want to use, I suppose, affinity propagation. In fact, I think I'm using that term incorrectly. I haven't looked up affinity propagation in a long time, but essentially, this is a way of creating or finding clusters such that you don't have to define the number of clusters at the start of the simulation. So k-means clustering, the problem with that is you have to define, that you're going to be clustering with k clusters, right? But affinity propagation allows the clusters to be created on the fly, so you don't have some hard limit of the number of clusters. Also, isn't there a presidential debate going on today? 1 second. There is one coming on, isn't there? 1 second. How to watch the first presidential debate live. Yep. It is from 9 p.m. to 10:30 p.m. Eastern time. Okay, so it's after stream. I will probably watch some of that. Over 1 million people have already voted. Oh yeah, as far as voting is concerned, I'm finishing up my absentee ballot stuff now. If you guys have not gotten on that and you are a part of the United States, are a citizen of the United States, do get on that. I think it's really important. Are you getting your popcorn out? Oh, for the debate? I do not know. I'm a bit worried about this. If I'm being honest, I don't very much like either candidate. Now, I do have a preference, and I feel a lot of people here also have a preference, and I feel like if you're watching this stream, you probably know my preference already, but I'm not going to state it here in this conversation. Point is, I am going to be very interested to see both of these guys talking to each other in any civilized fashion. It'll be interesting. We'll see what happens. Okay, the debate will be happening at 9:30 tonight. Feel free to check that out. Rosa Gold Glow Too Small. I don't know what that image is called. Okay, cool. So let's hop into Quiltify, CD Projects, Quiltify with a capital Q. And over here, CD Projects, Quiltify. And now we're going to do using, Julia _project, using revise. And then we're going to do using Quiltify. Okay. So we should be good to go. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. I do realize this is it's kind of a side topic. I kind of hesitate. I really like this. It's really cool. But also, like, I've got a feeling that this might be kind of, I don't know, it's not very clicky, is it? Like, coding up a quilt? I mean, I don't know. Anyway, let's just over here. VI source quantize. Okay, we've got a lot of stuff to try. We tried the HSV color space last week, and that didn't work very well because I failed miserably at it. So what I'm going to do is I'm going to modify the mutable struct color box here, such that it takes, such that we know the number of elements in the box. So here we're going to say pixels, or I guess we're going to call it n, and this is going to be some sort of int. And the idea here is that our color box will have a set number of particles inside of it, and to make sure this is working, what I'm going to do is, in our naive bin here, we're going to say count, no, I want to say box.n is equal to 0.0, just to be clear. And then down here, we're going to say box.n is going to be plus equals 1. And then down here, we're going to say divided by box.n. Right, this. So we're just going to create, what if it's -0? I don't know. I mean, I don't know. It's probably fine. Like, it doesn't matter if we're counting in floating point arithmetic or in integer. It's fine. Actually, wait a minute. I just said we were doing integers, didn't I? I cast it. Sorry about that. I cast it onto an integer. So let's just make sure it's always an integer. There we go. Perfect. So now let's try to create an image. So the image here is just going to be the pride flag, because that's apparently what we were using before. And let's just do a quick quantization on the pride flag, see what happens. I think we have to Control D, open it up again using revise. And now let's try it one more time. And see what we have. Now -0 is much more important. We'll see. Should be fine. I mean, in principle, I should be using a size t, but I don't actually know. Probably uint. I've actually never used a uint in Julia before. I almost certainly should have by now, but I haven't because I'm what you might call dumb. Okay. So we're going to let this precompile. Again, the precompile time is mostly in the images library. That just takes a while. And you'll note that if I do using images, images, and then image view over here, it'll take no time because we've already compiled them. Now we're going to say image is equal to this. If you're dumb, we are screwed. Oh no, you guys are screwed. So I'm going to do image view show, I am show. Perfect. Image here. And we should see the pride flag appear on screen in just a second. Oh, I was really hoping it happened when I snapped my fingers, but it did not. Okay. So now what we're going to do is img2 is going to be equal to quiltify.quantize, and it is giving me an issue for some reason because I don't know. So let's fix this. Line 8. Please don't tell me you're failing at line 8. Closest candidates are... Oh, I see the problem here. When I make a color box later, when I define color boxes later, I did not create a constructor for color box. So this means every time I call color box, I'm going to have to add a 0 to it. Let's try it again. That proves Simulatus is not a... Is that a witch? Is that a twitch? I'm not sure which word you're going for there. Okay, this is on line 80. And it says, witch, yeah, that's fair. Cannot convert object of type tuple to object of type int60. Oh ho. How the mighty have fallen. I don't know how that makes any sense, I'm sorry. I blame Simulatus as being a witch for making me mistype that. Fair enough. Burn-er? You know, I expected that you would have said burn-im, but you know, whatever, it's fine. So let's do I am show, I guess, image 2. There we go. So there we have our quantized flag. But I guess witches can only be female. That's fair. Well, is that true? No, witches can be male. Can witches be men? Okay, let's try that one again. Let's see. Can witches be men? Witchcraft. Female. Wait, can be male or female, but it's used predominantly for female. Okay. The book defines a witch as evil and typically female. The book became the handbook for secular courts through the Renaissance. Oh, this is interesting. I mean, thing I learned today is that let's see. Aiding the empowerment of young women through his lively portrayal of female protagonists. Fair enough. Female civilians in Syria. Yeah, so I think it's just like, you know how like when you play Pokemon, there's like a percent chance for you to find a male and percent chance that you find a female, right? I think it's like one of those things where you have like a 90% chance of finding a female witch and like a 10% chance of finding a male witch. So my guess is that, you know, they're mostly depicted as female, but like there is a chance for a masculine witch. Now, anyway, I don't know why we talked about that. I do apologize for that. Let's just keep going. What are you Googling today? CVC just said burn-er and said that regarding a witch. And so then I got a question, or I had the question, are all witches female, right? I thought a male was a wizard. I'm just going off of Harry Potter here. Yeah, I think that's a common depiction, right? Like typically wizards. So I suppose wizard, what's the difference between a wizard and witch then? What is the difference between... Okay, let's just see what everyone else is Googling. What's the difference between race and ethnicity, a lake and a pond, a pandemic and an epidemic, effect and effect, speed and velocity, Medicare and Medicaid, dementia and Alzheimer's, socialism and communism, Hispanic Latino? Those aren't bad. Those aren't bad at all. Witch and a wizard, warlock, sorcerer. Let's see. Magician. Okay. So let's do wizard. This isn't helping me. I was really hoping it would give me a... Okay. Wizard. There are too many wizards on this page. Gender-based title. Wizard usually refers to male, while witch usually refers to female. In Harry Potter, a man who anomalously showed the same abilities as a witch was called a wizard. The term wizard is sometimes used as a male counterpart of witch in fiction. However, either term may be used in a unisex manner. In which case, there will be members of both sexes bearing that title. If both terms are used in the same setting, this can indicate a gender-based title for practitioners of identical magic, such as in Harry Potter, or it can indicate that there are people who practice different types of magic, as in Discworld. Although technically gender-specific term used for a male witch was actually warlock. There you go, warlock. You learn something new every day. Okay. Well, Lord of the Rings, a witch is a bad and a wizard is typically good. Witch King of Angmar, for e.g., let's see, Merlin was good, his witch was bad, therefore all witches are evil and wizards are good. Interesting, in which case... the Warlock Wiki seems to genderize as male, referencing witches, which can be male or female. Interesting. So that's the opposite of the typical gender norm, because usually the way it works is you have a specific title for women, but you don't have a specific title for men. Like that's why. So, and again, you can ask why this is the case, but like in ancient texts, you would always say like him as the global him, and then you had another term which was wir, W-I-R, that was meant for men, I think, if I'm remembering correctly, for English. But I might need to look that up. W-I-R, men. And so I thought that's what it was. But it used to be in ancient English, you had a word for everyone, which was basically he, and then you had a word for women, which was she, and then you had a word for men, which was something else. I want to say it was were. But then he became masculine, and she became and she was always feminine. And so what I mean by this is that the way in which the English language has evolved usually happens the other way, where there isn't a specific term for male. And of course, there's questions as to whether there should or shouldn't be, specifically gendered terms or not. And I'm not getting into that discussion. I'm just saying that's what that I don't know. I'm just saying stuff right now. I need to get back to programming. Nick C, thank you so much for following. Really appreciate it. M or F or hermaphrodite. Pardon, miskey, correction, male or female. Right. Good. Okay. So we have already done stuff today, which is good. If we do nothing else, we have at least changed 2 lines of code. So we're getting there. Okay. So we've got like 5 to-dos to do. So take n most populated boxes. Some boxes return negative mean colors. So quantization may fail if no colors for a box. Okay. So let's start with this naive bin function. So this is the thing that's taking most of my time. I'm like 90% sure this is the thing that's taking most of my time in the quantization step. And the reason I think that is because literally all I'm doing is, in order to determine which bin, which box my particle is in, I look at this box, and then I go through every single particle in the simulation. Every single particle in the simulation, and or every single pixel in the image, and I ask, hey, is your RGB value within this box in here? That was dumb. Within this box in here, or not, right? So that means any pixel that is not in that box is still, right? So the box has some number n, n pixels inside of it, right? But the entire simulation has some big N, right? And so basically we're doing way too many counts. Every time step we're doing like n minus n, big N minus little n. Wow, I'm doing a bad job of explaining this. Big N minus little n checks to see, hey, is this particle in the simulation or not? When we don't need to do that. We only really need to check. If I need to think about that. So the question is, how do we know what our little n is? Does that make sense? How do we know which particles to check? How do we know which particles to check? That's my question. How do we know which pixels to check? That's a very good question. So journal, new page before. So the way this works is we have a box, and inside of the box we have a bunch of mini boxes, right? So we have, a mini box here, mini boxes here, something like this or something. So then this is again split up, so we have here, and that's again split up, so it's here and here. And just to remind everybody, when we're splitting this up along RGB space. So this is R and B, for example. We're not splitting up in pixel space. So this is not the same dimensions as the dimensions of the image, which are X and Y, right? So what we're doing is we're going through all the pixels in the image, and we're looking at each pixel's RGB value. We're then putting that RGB value of, let's say, this pixel over to wherever it fits over here, let's say over here. And then we're trying to figure out, hey, how do we know? We're trying to figure out if there's a way for me to tell if this pixel, or rather, if this pixel is in this box without looking at it too deeply, So I think what we could do is we could take all the pixels in the image and we could sort them. It gets complicated, right? So like the point is, up here is more red. So this top is like more red up here. And, I meant to do that in red. So this top is more red. And this side over here is more blue, right? So it gets complicated because if we're looking at all the particles in the simulation, all of the pixels in the image, we could sort all the pixels based on their red, their green, and their blue. We could, so essentially we just have an array of RGB values. That's what we have right now. That is what an image is, an array of RGB values. So if we've got an array of RGB values, the question is, how do I know that RGB value, how do I know what bits in that array fit into like this box over here? That's my question. LXOR, that's my question. I've got n pixels, right? Where n is the number of pixels in our image, right? And the question is, how do I know which pixels go into which box without just looking at all the pixels? Now, clearly what I could do is I could say the parent box, let's say the big box here, hopefully you guys can see that, has a certain subset of pixels inside of it. And then instead of having to look through all the pixels in the image, I just look through all the pixels that are in the parent box. You need to know width versus height. Well, we know width versus height. What do you mean? No, we know width versus height, obviously. That's not an issue. The issue is that this is a different space completely, right? So this is like Cartesian indexing, right? So let's think about this a different way. So let's think about it as we have an array, and this array stands for a number of different particles in a box, right? So here's all of different particles in the box, right? All of these guys here. Looking at the parent box and shrinking them down is a binary search. I think it would be if we were on an array, but again, we're not an array, we're in Cartesian space. So that makes it so this is a bit different. Okay, so again, we have an array, and let's just say the array is filled with xy values. So xy, 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 something like this, right? So what I need to do is I need to figure out, let's say, oh, there's probably some good binning algorithms. Let me look up some binning algorithms. Binning algorithms. Has to be something, right? Okay. I was hoping data binning. Histograms are an example of data. Yeah, I know what data binning is. Binning is a procedure of combining a cluster of pixels into a single pixel. As such, in a 2x2 binning, an array of 4 pixels becomes a single larger pixel. Reducing the overall number of pixels. This aggregation, although associated with loss of information, reduces the amount of data to be processed, facilitating the analysis. For instance, binning the data may also reduce the impact of read noise on the processed image at a cost of lower resolution. Yeah, that's fair. I was hoping that there was something a bit more visualizing. No, this doesn't help. What is optimal binning and how is it done? Problem. The SPSS and Clementine have a new procedure called optimal binning. Please explain the concept of optimal binning analysis in situations where it's useful. Surely if you want to find all elements in an array that fit a certain category, you have to look at all of them. Yeah, it might be just what we have to do. We might just have to look at all of them. But maybe there's a way. So right now what we're doing is we're looking at every single box, right? So the naive bin here takes an image and takes a box. It goes through every single pixel in the image and asks, is that pixel inside of this box, right? Maybe there's a better way to do this where we look for all of the boxes at once, right? This is a micro optimization. You're still in the same order, but the idea there would be instead of looking box by box, you look at all the boxes' children. So this would mean you look 8 boxes at a time instead of 1 box at a time. In fact, let's just go ahead and benchmark this guy and see what is actually taking the longest amount of time. So let's do add benchmark. Let's just go here, add benchmark tools, and let's just do an add benchmark here and see what's taking the most time. Because I think that'll be helpful here. Because maybe we don't even really have to update the naive bin. So we've got the image, we've got the box. So we also have the make octree function. So what I'm going to do is, where's our make octree? Make octree takes image and max level. And then if I do color quantize, down here is image and color number. So let's go ahead and do quantize. So we're going to do using benchmark tools. So let's try this first, and now we're going to add benchmark, Quiltify dot quantize, and we're going to do image, and let's do 9. Yeah, I think that's what I want. At benchmark, benchmark. Oh, what's your issue now? Quintize. Oh my gosh. All right, let's do that. All right, let's see what happens. Again, if you guys have any questions, comments, concerns, ideas, anything like that, feel free to let me know, and I will totally address it as soon as I see it in chat. Okay, so it's kind of doing its thing. It's going to do a few runs, I imagine. I'm not really sure. We'll see. It's obviously doing more than one run. So, and then after this, I want to do a benchmark on specifically make octree, just to see how long make octree is... Okay, so this says it takes a mean time of 3.727 seconds, medium time of 3.727 seconds. It only took 2 samples, so this doesn't really help too much. But that's okay, 3.7 seconds is about right. So the next thing I want to do, make octree. So quiltify.quantize, so now it's going to be make octree on the image that we're looking for. And the next thing I want to do is the max level here is going to be... we wanted 9, so the max level here should be 2. Yeah, this should be right. I'm doing way too much print line, like, output. Maybe if I just didn't do that, that would also save a lot of time, but we're not outputting that much, so it should be fine. Okay. So the last one was 3.7 seconds. So I'm expecting this to be most of the time. I'm expecting this to be like 3.6 seconds or something, 3.5 seconds. And again, what I'm trying to do, so this is it's literally basically 3.7 seconds, right? So we have make octree, and then we have divide octree, and within divide octree, we then have naive bin. So we should now have the octree. So let's go ahead and create that octree. So we're going to do benchmark. We want to do tree is going to be equal to that. So now we're going to have the tree and all of its children. And then we can just try the divide octree function. No, we already have the tree. So now we can do the naive bin function on the image in the box. So let's just do at benchmark Quiltify dot naive bin of image, and then the box is going to be just tree, which is what I called it. Let's see how long that takes. And yeah, I should probably remove a lot of these print lines and just see where we go. Yeah. So as far as streams later this week are concerned, I am going to be trying to stream. So tomorrow is probably going to be a long day dealing with graph structure and stuff like that. I know that sounds a bit weird, but my lecture on Thursday is all going to be graphs. So I'm probably going to do like a 4-hour stream tomorrow just on understanding graph structure and how to use light graphs and all that kind of stuff. I meant to do a lot of that today, but I ended up being in meetings until, well, basically now. Well, until 6, so just before stream. Okay, so obviously this naive bin is taking the most amount of time. So let me try to modify this a bit. So we're going to create a new function, which is, again, function naive bin. I'm going to call it the same thing. And we're going to take in the image, and we're going to take in the set of boxes. So we're going to say children, which is of type vector of color box. In fact, I probably should specify down here that this box is of type color box. And then we're going to end this in here. We're going to do a very similar thing. We're going to go through all the pixels in the image. But I think what I want to do is at this step, iterate through all the boxes and go through there. So let's just go ahead and copy this and go up here, and let's just work on this for an array, and then we'll see what happens. So this basically just means that we're going through all the elements in the image and all the boxes, all the children at once, rather than doing them one box at a time. I don't know if this is going to be any faster. It just means we iterate through the array less times. We only go through it once instead of going through it 8 times. So maybe this will help. So we say 4 pixel in image, and then we're going to say 4 box. Box in children. Sure. And we're going to say if in pixel. And here. And there. All right. So now we're going to say 4 box in children. And now we're going to say down here, 4 box in children. Go down here and say. Okay. Now, one thing I think is going to happen here, Josh4FF, thank you so much for following. I feel like I'm not able to modify the contents of box in children here. Let me check that really quick. So let me create an array. A is going to be equal to, we'll just say zeros of 10. And now we're going to say 4 element in A we're going to say a is element is equal to 1. We'll say, yeah, 1, why not? And if I say a, yeah, okay, that doesn't work. So now we're going to have to say for I equals 1 to length of children. Just do it this way. Children of I, and then let's see, box.color. If we're going to have to change all the boxes. Sure, that's fine. We'll just do that. So for I equals 1 to length of children. What is color box struct again? The color box struct is up here. It's just a union of RGB nothing. This basically says this is the mean color. I probably shouldn't have called it CLR. I should have called it color, COLOR, but that was taken by Julia. Then children, which is the number of sub boxes. N, which is the number of elements in each, number of pixels that fit that box, and then the extents as well. We could also put a vector of like a vector of pixels within the box every time, but I feel like that's a lot of things to keep track of. So, okay, or I could spell color correctly. I think I am spelling color correctly, so you can just deal with it. I'm joking there. I don't really care about spelling. Children of I. All right, let's just do that every time. Here, there, there. Well, you're just wrong. Look, man, here's the thing. Like, never in my life have I heard an American... okay, this is going to sound really weird. Okay, IHQMD. I have actually never heard an American get pissed off at European spelling, but I've heard a lot of Europeans get pissed off at American spelling, you know? So, like, I mean, I understand that, like, and also, like, metric and stuff like that. So, like, very few Americans are like, you know, Celsius is, like, very few Americans don't like the Celsius system or something like that. Lots of them really like it. But, a lot of, like, Europeans are very snobby about it. Like, they're like, you know, how dare you not use metric? I'm like, well, it's not my fault we're not using metric. We're just not using metric. I personally use metric. I know I'm 175 centimeters and 70 kilograms. I know that. It's easy to remember. I don't know my height and weight in non-metric units, but, like, there's no reason to be snobby about it, you know? Well, I was thinking you could have a vector of pixels, and then instead of iterating over the image each time, you can then iterate over the pixels in the parent. Yeah, so I was thinking that as well, but that's a lot more data storage. And so the question is, do you want to, I mean, that's memoization, right? So the question is, do you want to actually do that data storage or not? I don't know. I'm in Australia, we still use color when coding. Yeah, see, WX widgets, it actually has color in the API. Fair enough. Okay, so now what I'm going to do is go down here. Right, so again, the question is, do we want to store more data in each node? We could. Let's just see what happens if we do naive bin here, but we do it over the children. So we have children.extents is equal to that. You could then further optimize if you had no pixels in the parent. You can stop dividing. Right, that's true. So divide octree. Actually, the way I have this written does not allow for me to even use the naive bin function that I just created. Because this assumes that I've already defined the children extents, the child extents, which I have not at this point. So we have, let's see, naive bin. So then we print line children of color, then we divide octree on that child. Ooh, okay, that doesn't quite work, does it? Oh, you know what? I can just do it the dumb way. Let's just see what happens. So we're going to comment all of this out there and comment it out up here. I'm really just checking to see if this is any faster. So I feel like insisting on metric is very different in nature from insisting on British spelling. Maybe you're right. Maybe I again, like, for the record, I'm not against anyone in chat. I quite like the conversation in chat. I'm not saying that the color, like, spelling of color matters, you know? It's just that I've just noticed that a lot of people are quite snobby about it, and it kind of gets me a bit, I don't know, a bit, not miffed, I'm just... Oh, no? DDP. Let's do DT here. Print line, and then children of I. Should work. Okay. Yeah, whatever. Let's just see what happens. So we're going to do image 2 is going to be equal to Quiltify, Quantize. That didn't work. Why didn't that work? It says invalid identifier. Okay, let's just do revise dot. Oh no, the thing is an R. Retry. Here. Invalid name. This is on line 51. It doesn't like. Oh, I need to do children of I. Try that again. Okay, great. Now let's try this and see what happens. Box not defined. Okay, that is on line 153. Here. Oh, what? Okay. That is on line 121. There. Image box make octree. Box is equal to color box. 94. So now you've been image children. Oh, probably box.children. Try it again. Box not defined. Right. Okay. I'll catch up on chat in just a second. Box is not defined on line 94. Here, box.children. Box.children. Box.children equals children. Okay. So what was the issue before? Children. Try that again. Error box not defined. This is on line 35. That is box.n. Oh, that's because, okay, I gotcha. I understand now. Go over here, image 2. Okay, it's doing something. Hopefully this will be the same image as before. Something clearly broke there. Or did it? No, let's call this image 3. Well, let's do I am show image 2. Okay. Image 3. Oh, image 3 is equal to that. Because that was super quick. And now we're going to do I am show image 3. Okay. So that was way faster. Like, way faster. Okay. I'm a fan of that. So let's try doing image 3, and this is going to be equal to 65 or something. Okay. Let me catch up on chat. One is clearly more justified than the other. By the way, I live in the UK, and I don't really care about American spelling. I'm not a fan of using words ending in I's, though. Yeah, that's the thing, right? Like, I like the Z. I understand that other people don't like the Z. It's fine. I don't care. Add a card. I still think the metric system needs to switch stuff. So the kg is the G, and as such the SIU. Oh, I see. Like, you don't want the kilogram to be the main unit. You want the gram to be. I guess I's is closer to how it's actually pronounced. Not that it really matters for English, right? So I do feel like American English is easier to learn than British English, like in general. Because, like, again, I-Z-E, that's how it's pronounced. You know, like, Z doesn't make any sense because why would you call it Z instead of Z, right? Because, you know, beta turned to B, eta turned to E. You know, all the other ones that are like eta, beta, theta, you know, all this kind of stuff. Well, not theta. I guess theta isn't in the English, English alphabet. So... yeah, everything is base SI metric except kilogram. Also, Aussie English is where it's at. That's also fair. Z is not used in British English. Maybe not. Coding a quilt. No, coding a quilt. So the idea here is that we're taking some image, let's say this image up here, and the first thing we're doing is color quantizing it, which is basically selecting the set of fabrics that we want to use for our quilt. Then after that, we're going to turn it into quantized like quilt pixels or quarter squares. And then after that, we're going to apply that texture to it. So it's literally just coding up the steps in order to go from any image to something that you could sew up onto a quilt. That's what we're doing. It wouldn't be hard to make the kg and the g. It wouldn't be hard to make the kg the g and just use milli, micro, nano. Yeah, that's fair, I guess. Portuguese English is where it's at. The thing is kilogram. So the reason kilogram is so important, I would say, is because of the physics, essentially. So kilogram being the SI unit for physics, it makes a lot of sense because the Newton is defined by kilograms, right? So it's like 1 kilogram meter per second squared. So the Newton is essentially the force that 1 kilogram applies, essentially. So because of that, kg, I think makes sense specifically for physics. Although, for chemistry and stuff, it makes way more sense to use the gram. So it just depends. Plus, kilogram is a much easier thing to hold, I think he means to define the new gram as... Oh, I see what you mean. I misunderstood. It defined the new gram as 1,000 old grams. Yeah, if you could do that, that would also make sense. But look, I mean, that's actually way easier to do than like convert all of the US to the metric system. Converting all of the US to the metric system is quite hard, which is why it's clearly not been done up to this point. Okay. Idle card, thank you. Much more comprehensible than me. Yeah, I appreciate that. Thank you. Then all SI units would have to have no pre or suffixes. I see. Yep, I understand what you mean. Okay. Well, this naive bin is already way faster than the previous naive bin. So in here, we're just going to say small improvements. Oh, well, actually, let's just benchmark this. Okay, so we're going to do one of the last at benchmarks. So the last one took 3.7 seconds. So if we do at benchmark make octree 2, the last time it took 3.7 seconds. This time it's going to take... Give it a second to do all the benchmarks, but I assume it's going to take way less than 3.7 seconds. And again, we could improve it further. Could be made by only iterating through elements of the parent node. So we can try that as well and see if that's really worth it. Oh, that also took 3.7 seconds. Did it really? Oh. I think it just felt quicker because there was less being output. And because there was less being output, it felt quicker. But this actually was slower. All right, let me just make sure I'm not dumb. So I'm going to go down here, and we are going to change this to what it was before. DD here, paste up here, and then go down here. And then go here, DD, write that, and now we're going to try tree is going to be equal to make octree, just so we do it once. Converts an image to a quilting pattern. Yeah, that's essentially what we're doing. So let's try at benchmark that. Okay, so the last one was 3.7 seconds. This one is probably going to be the same speed, which says to me that it doesn't matter which way we go. Like, we're still doing the same number of operations. Again, the optimization here would be that we basically give each parent node a vector of pixels that fit into that node. So if this is about the same speed, I'm actually just going to revert the changes we just made and commit the changes that we made at the start of stream. So that's 3.724. The one before it was 3.722. I'm going to do one more benchmark of this guy, because honestly, we did not, like, basically all that code I just wrote was for naught. It was completely useless, which is fine. It's totally okay to have useless code. No, it's not. Time to rewrite in C. No, I think this is about the same speed you'd get in C, honestly. Why do you expect them not to be the same speed? So by taking it out of the loop, we iterated through the pixels in the image fewer times, essentially. But you're right that inside of each... Yeah, so 3.61. Yeah, so you're right in that inside of each of these guys, we did check for every box. But I thought that the checking for every box... So I thought that checking to see if the element was in a box or not was a negligible cost, because that's basically just a true-false evaluation. Like, the inbox function is relatively straightforward. Meanwhile, I thought array accessing would be a bit more costly. So what I did is I made it so you only access each pixel in the image one at a time. And then after that, you then just do an evaluation for each box on the pixel. So apparently, in this case, it doesn't matter. They're both about the same. This is Julia. The language we're using is Julia. So Julia is about the same speed as C, with, rough. It's within an order. It's within the same order of magnitude as C. If else branching is much slower than array access, that is not true. What? That's not true. Conditionals versus array accessing. That's definitely not true. If you're doing a non-coalesced memory access, it's way slower to do a conditional. Or it's way slower than doing a conditional. Testing for membership. The only time you really have to worry about branching is if you're like, okay, so I'm coming from GPU logic, but the only time you really have to worry about branching is if your warp is if your warp is not aligned. So that would mean that you have to do 2 operations instead of 1. RAM is slower. Yeah, see, RAM is definitely slower, right? Cache access is faster. I'll agree with you there. But here we're sitting on RAM, so it should be slower. I mean, unless I'm completely dumb, which I could be. Like, don't get me wrong, I definitely could be. But yeah, non-coalesced memory transfer or non-coalesced memory access should be really slow. Again, I'm thinking back to GPU terms though. So on CPUs, I'm not as confident with CPU logic. Regardless, this is basically the same speed. So I'm just going to get rid of this bin function because clearly that didn't help. Let me go ahead and remove this here. Okay, and let's remove this stuff that I wrote here as well. And so we're just going to go back to this, write and quit, git status, git add source quantize, .jl git commit -m. What am I going to do? Git commit -m. What did I change in this file again? I did one thing and I forgot what that thing was. Let me do a git diff source quantize. Oh, head? Is it head here? Okay, great. So, right, so what I did at the start of stream was I made it so, made it so each box has a count of the number of pixels. So git commit -m, modified color box struct. So each box also has a count of the total number of pixels. Whoa. Sure, okay. That's a dumb commit message, but it is what it is. Git push development origin. Okay, so the reason I did that is because development origin development. Sorry about that. Okay, so we're gonna make some larger modifications next to see what we need to do. CPU logic 1 + 1 = 0. Moving a page of memory in RAM takes as long as a floating point multiplication. I think I read that somewhere. Could you provide a source for that one? So, because I'm interested to see whatever you read, I'm interested to read that same thing. Like if it was in a book or something like that, I'm interested in reading that book. And also, it's probably somewhat language specific. So I'm not sure if Julia. I mean, I would imagine Julia uses LLVM underneath, so it probably follows similar logic to C in that regard. But also the fact that Julia is a garbage collected language maybe does something with that, because I'm just so used to dealing with my own memory. Garbage collected languages just kind of boggle my mind a bit, you know? Like I'm very used to like freeing my own memory and all that kind of stuff. It'll be buried in my internet history somewhere. Don't worry about it then. It's okay. Don't worry about it at all if it's too much effort. Okay, so now let's try doing the next thing here. So we're going to have extents, and then we're also going to have a pixel set, is what I'm going to call it. And it's just going to be a vector of RGB values, something like that. But does that not fall over as more and more crap is being hardwareified? What's being hardwareified, actually? I feel like, if anything, most stuff is relying more on software than hardware nowadays. But maybe I'm misunderstanding. So color box here, color box, and so here we're just going to give it a blank vector. Next, so color box here again, we're going to give it a blank vector. Okay, and what I'm going to do is I'm going to see if this runs as is. I think it should. So we're going to say image3 is quantize. That was no method matching, make octree. Let me just do revise.retry. And it says it's on line 153. 153. Not that many lines in the buffer. G. Okay, so it is on set number. Set no number. It does say it's on line 153 though, right there. Quantize the JL, line 153. No method make octree of array RGB normed int. Control D. Let's just try running it again. Why not? What's the worst that could happen? What editor? I use VI. There is a Simul VI here in chat. We have an emote for it. It's just Vim but colored red and old school. So now we're going to do using... I'm in the wrong terminal. Using Quiltify. All right, give that a second. Vim is not the devil. I quite like Vim. Let's see. It would be a lot... Let's see. Alex Lower, but that does not fall over. It would be a lot of gates for a float multiply. Now the low level stuff, see AVX 512. Okay, yeah, you're right. Right. Yeah, I agree with that. What I read was definitely general purpose registers, not faster SIMD registers. Okay, so we have Quiltify using images, image view. Okay, let's see what happens if we do image. First we have to define the image, and that's going to be equal to load the pride flag, because apparently we're just doing pride flag. Are those colors? Hey, Buttercake, how are you? Hope you're having a great day. It's been a while. How have you been? Okay, so this is running, but also I'm doing 65 colors here, so yeah, might be too many colors. We'll just kind of go over here to this terminal and just kind of go. I just got a message from work. Okay, I don't think I have to respond to this immediately. Okay, great. Let me respond to them really quick, and then I can keep going. Okay, great. And we should be good to go. Floating point ops on AVX are only twice as slow as integer arithmetic, which is quite insane. Oh yeah, actually, that's quite cool. So we have image 3, so let's do IamShow of image 3. Give it a second to precompile. Yep. Almost there. Eston, hey, how are you? I hope you're having a great day. How was your stream, man? Christian Iverson, hey, how are you? So today we are doing, right as the pride flag appears, we are doing basically code to create a quilt. I know that sounds really weird, but hear me out. So we want to take any image and we want to basically turn it into a quilt pattern, right? So this encompasses 3 distinct steps. One is color quantization, which you can see up here on the left, and is currently the step that we're on. The idea here is that we take any image and we create some subset of colors that allows for us to kind of span, like we find some subset of colors which are like the most popular colors in the image or something like that. And then we basically take every pixel in the image and we cast it onto that set of colors. So that's the idea. So that's what we're doing first. After that, which will probably be done later this week or next week or whenever we get to it, we'll be working on the next steps, which would be to kind of turn any image that we have after the colors have been quantized into a quilt-like thing. And then after that, we will then apply some sort of texture to it. So we've got a lot of steps, but we're kind of making progress one step at a time. So right now we're doing color quantization. The way this works is basically by taking any array, which could correspond to an image. So an array of RGB values, which corresponds to an image. And we say that every single point in this image over here has some sort of RGB color, and that can be put into some sort of 3-dimensional RGB space. Then after that, what we do is we kind of split up our 3D RGB space in half, and then in half again, and half again, and half again, into an octree structure. Here's a quad tree, and we basically keep splitting it up again and again and again until every single point has its own box. At that point, we can basically tell what the average of each box is, and we can say, well, if this box has more pixels inside of it than this box, Presumably what we can do is we can assume that's a more important color, and we can use that for our color quantization. Fraser T1, thank you so much for following. Really appreciate it. But yeah, Esden, I hope your stream was great. Again, if anybody has any comments, questions, concerns, ideas, anything like that, feel free to let me know. And yeah, so okay, let's keep going. So right now we're going to be trying a bit of an optimization just to see if we can speed up the creation of our octree. And yeah, we'll see how that goes. Esden sounds very interesting as always. Yeah, man, how was your stream? Let's go up here. Also, you don't have to say how your stream was. Anyone who's here and you like my kind of content, you're probably gonna like Esden's type of content as well. Go follow them; they're great. Yeah, that's all I have to say. I always feel bad about talking about my stream when I raid other people. Like, I'm actually kind of like a bit hesitant to raid people because I don't want them to talk about me in the stream. So it's kind of like a weird, I don't know. I get kind of, I understand if you don't want to talk about what's going on. I need to stop egging people on, you know. So what am I doing with my life? I'm gonna do something. So we're gonna make it so, oh my gosh, what am I doing? I just got completely sidetracked. So we have this naive bin function, which takes the image. What I want to do is make this naive bin function take a set of pixels. So we're just gonna say pixels here, and down here we're gonna say pixels. All right, and what we're gonna do is we're gonna say if box.color is equal to nothing, then we change it to that, and now we're gonna say box. Ooh, this is gonna be a bit annoying, isn't it? Box.pixels. I think I called it pixel map. Is going to be equal to the vmap. Oh no, how am I going to do this? Vmap. How do I append? Like append array in Julia. There's no way this is going to be faster. With all these array appending, it's going to be way slower. There's just append. So we're just going to do append. Here, append there, the pixel map with the pixel. There. And I believe I did call it a pixel map. Pixel set. Let's see. My stream went well, and we finally got some more work done after weeks of busy with other stuff. I totally hear that. Simulators get sidetracked? Never. How dare you say such blasphemous things? Sidetracked is foreign to Simulators. I don't... In fact, just for the record, I don't think I have a normal tract. I think that I have like an infinite number of tracks that I could be on at any given point in time. And none of them are actually a side track. They're all just separate tracks that I could decide to go on, you know? Well, what I meant is that branching is not inherently slow, but cannot be done in parallel. Right, that's true as well. Okay, good. So that was the guy from work. Great. I get distracted all the time during my stream or go on some strange rant. Oh boy, let me tell you about strange rants. Should we go on a rant about how strange my rants are? No, we shouldn't. So now for divide octree, what I'm going to do is I'm going to say for this naive bin, we're just going to say, I believe I can do box.pixel set, box.pixel set. And I suppose what I want to do down here is for the initial box that we create, I'm going to say this is image. All right, let's see what happens. Image 3 is Quiltify Quantize 65. Yes, that's an error. Thank you. Okay. It is going to be on line 118, 83, 83. Right. So the issue is that, oh, okay. This isn't a vector. It's an array. So maybe I just need to go up here and just say an array of RGB. And I might need to, yeah, I might need to revise.retry. Redefinition, yep, so I have to load it again using revise, and now using Quiltify, and now give that a second to precompile, and then we go from there. We get an education on witches from Simulators earlier. We got one. Hey, look, I was interested, like, what makes a witch? Does a witch have to be a girl? I don't know. I mean, could I be a witch? I'm pretty good with nothing. I was going to say magic. I was like, well, I'm not good at magic. Then I was like, programming, but I'm not very good at programming. So it's like, okay. Using images. Okay, using images, image view. And now we're going to do image is equal to that. And image 3. Image 2 is going to be equal to Quiltify 9. This is broken, which is good. So now we're going to do 83. It says in new expected array of RGB n, where n got a array of RGB normed uint 8. Huh? How about we just call it pixel set? It is of type any now. We have to do this whole thing again. So using revise. Okay. And then everything else. You're pretty good at programming? You can. Some people in chat don't think that. Using Quiltify. All right. Then we're gonna do using. Oh, it takes so long. Julia, my man, you are just my person. I shouldn't be sexist. My person, not my man. Trying not to be sexist here. Also, with a name like Julia, my man is probably not correct. Oh well, it is what it is. You're very pretty good at programming. See, that is more what I expected. You're very at programming. Using images, image view. And now we're going to do what? What are we doing? Give me just a second. I need to think. We're going to load the image again. We're going to load the image again. And then we're going to do image 2 is going to be equal to Quiltify to quantize. Image not defined. That's okay. This is better. 72. I don't see how you're on line 72. Let's go to 40. For pixel in pixels. Try that again. Hopefully this works. It's just a tool as long as it gets the job done. Yeah, that's true. Array has no field extents. Okay, let's go to line 26. If in box, pixel box, so for pixel in pixels, where are we using, so inbox, if inbox pixel, oh, I see what I did wrong. If inbox pixel in, and I need box, is what I need. Yep, that's what I need. Try it again. Okay, one day this will work. This is on line 47. Append box pixel set pixel. It says iterate. It doesn't like append here, and the issue is that no method matching iterate. No method matching iterate. Pixel set should be an array. Iterate RGB normed. Can I not append a is equal to this? And now let's just say RGB of 0. And let's just do append here a RGB of 0. Close parentheses. Okay, so we got the same error. That's nice. So now let's say A is going to be equal to array of RGB. And now we try append A. Okay, good. It's just a tool. I would probably use Julia if it wasn't for the error messages. I don't know. Error messages are a thing. Julia has error messages. Like, you want a programming language without error messages? I mean, oh, we should do that. We should make a programming language without error messages. Then you can never be wrong, right? Let me get some water. So it turns out we can't append an array. It just does not work. No error. Yeah. So, right. So apparently we can't append. We could pre-allocate the array. We could just say, we could pre-allocate. Okay, look, this is just a test. This is just a test to see if it works. So let's go here and we're just going to say that every number for Python has much worse error messages than Julia. To be fair, the error messages specifically for GPU computing with Julia are really bad. They're just not very good. Okay, so we're gonna have half the time it's just a lowering error. Oh no. Okay, so we have, let's see, I equals 1, I equals 2. I don't know why I'm just reading random code. So we've got our pixel set. And the issue here is we can't append here. So is there a way to pre-allocate? Is there a way to pre-allocate the array? The answer is yes. So let's just go ahead and do that. So we're going to say box.pixelset of, I guess I is going to be equal to pixel. And I guess what we're going to do then is we're going to say for pixel and pixels. Oh, actually, we can use box.n. That's what we can do. Box.n plus 1. Cool. Okay. So when we initialize these guys, we're going to say all the children are going to be of size. What happens if we iterate through a nothing? So A is going to be equal to array of, oh, this isn't going to work either. RGB. No, this ain't going to work at all. 0, 10. It's not going to work at all. Yeah, because we don't have an array initializer for RGB types. Okay, this is a bit more complicated than I thought. So for pixel and pixels, so we're going through the box. Oh, no. We're going to do this in the dumbest way possible. We're going to make it so every single one of the children has an entire image stored inside of it. Is this dumb? Yes, it is. Will it work? Probably not. But that's okay. Let's just do it. So we're going to do box.pixelset, where the pixel set is going to be equal to 1 to box.n plus 1. Image 2 is Quiltify. Oh, did that work? That maybe it worked. Image I am show image 2. Did it work? Come on. I would think that that is not working, personally. Okay. Let's see. Yeah, I guess I only use compilers, so those errors are nice and concise. Else it's segfault time. Oh, segfaults. You gotta love segfaults. I like React's error messages. They tell you exactly what's going on. The whole interpreter stack trace dump just hurts my brain. Tomato concern, verbose not equals good. Yeah, I agree with that as well. Also, a lot of times the Julia's backtraces don't actually show you the right line for the error. Like, the errors are just not very good in Julia. But, you know, I feel like the fact that you can, how do I put this? The fact that you can iterate so quickly between code and the REPL and stuff like that, I feel like, fine, it's kind of a fair price to pay. Bad error messages, but also it's a lot easier to debug than just, you know, going through GDB or whatever. Actually, now that I think about it, I do think that the C... This is exactly the same thing I would do for C or C++. I just type make every time, instead of just running it in the REPL. I get plots easier in Julia. There's that. That's nice. The language itself has a lot less boilerplate code, which is also nice. Yeah, those are the advantages, really. You get plots easier, but also I don't usually use Julia plots. It's actually surprising that I am using Julia plotting now. I don't know what that first word is. Errors are very nice. It actually tells you wrote a wrong thing. Did you mean XYZ? It is more often than not correct. You have to sell your soul to use Julia. Not so nice. Also, I did kind of realize the error messages in C++ recently do give you like expectations for what they thought you were supposed to write. So in that way, the C++ error messages are actually a lot nicer. Man, you guys are making me want to go back to C++. I like C++ a lot, but let's just keep going. Let's keep going. What if I just make it box n? Image 2. I show. Okay, now it's just black and white. Box.n is the total number of... Do you use LLVM or GCC? G++, so GCC. LLVM, I mean, Julia uses LLVM under the hood. Rust tells you exactly what you should have typed. Interesting. I've been slowly moving my way towards feeling okay with the idea that I could potentially try Rust in the future. That was really loopy. Rust learned a lot from Nat developer messages. Rust takes 10 years to compile stuff in it. Oh, yeah, well then it's not a useful language, right? If it takes 10 years to compile anything. Like, look at me using Julia over here. Okay, I feel okay with the idea that I might potentially try it. Oh, man. That is, like, the least committing, like... And they say guys don't have a fear of commitment, right? Okay, no, wait, they say guys do have a fear of commitment. What? What do they say? I don't know. I've never really known what they say. Okay, so we're saying box.pixel set of box.n plus 1 is equal to pixel, right? So it's going to be 1, 2, 3, 4, whatever. And then we're adding 1 to n. Oh, this should just be box n. Try this again. And then let's move down here. It is probably... I'm going to guess... No, it's just box n. Okay, let's try this. Image 2. Image show. No, it's still black and white. Dang it. For the projects of the size of what Simuleos does, the compile time is not an issue. Right, that's also fair. But, okay, to be fair, I also do a lot of like supercomputing stuff, and I do a lot of stuff with Klima. Stuff I do on stream, probably Rust wouldn't be too bad. Stuff I do for work, I don't know, really. Getting much faster. So is a grandma on a Zimmer frame? I don't... Even for small project, and I disagree that it is painfully slow. Yeah, also fair, right? Like, again, we can argue about languages and stuff like that. We really probably shouldn't get involved with language wars. So we do naive bin, and it's gonna be box.pixel set 1 to n, and we're gonna say children of index. That should be fine. So we're doing the naive bin of each child. That should be fine. So our pixels should be. Oh, I do see one problem though. Down here, our initial thing should have n set to be length of image. Try this again. Image 2 with Quiltify. All right, so now we're taking time. All right. So now I believe this did work. If we show image 2, that's exactly what we wanted to see. Perfect. So let's do a quick benchmark of Quiltify make octree image using benchmark tools. And now let's try it again at benchmark, and we're looking to beat 3.6 seconds. That's what we want to beat. And this should, in principle, beat it. I think. I think so. I think it beat it. I'm going to guess 2.7 seconds. That's what I'm going to guess. I'm going to guess a full second faster. It's like a blanket. Yeah, that's what we're doing. We are coding up something to take any image and turn it into a quilt template, so you could sew it. 3.6 seconds. It is the exact same speed of what we did before with a crappy implementation at much... Okay. Yeah, that's... Okay, that's fine. That's fine. We're just going to go back to the previous implementation because this didn't work either. Okay, so for those of you who may have just hopped in, you haven't been watching the stream, we are making a quilt today and tomorrow probably as well. The idea here is that we take any image, and first we color quantize it, which is basically finding the set of fabrics that we need in order to make the quilt. So as you can see over here on the left-hand corner, upper left corner, we're taking any image and we're compressing it to first 64 and then 8 colors. So we're finding the set of 8 colors that are the most used colors in the image. And then what we do is we select those colors to use for the image, so we cast all the pixels onto that set of 8 colors. Now this helps because it gives us a set of fabrics to choose from. Then from there we have to pixelate it, which is we're going to call Quixelate for quilt pixels, which are the same as normal pixels except that they have quarter squares as you can use quarter squares instead of just full squares, so that's kind of cool. And then after that, we just have to apply the texture, and we'll be able to take any image and turn it into a quilt. The color quantization here is probably the hardest step, which is what we're doing right now. Hence why we're spending so much time benchmarking it and testing different things. That's a 2.7% speed improvement. But let's run it one more time, shall we? Let's see if we still get 3.606 on the second run of benchmark. So yeah. Anyway, again, guys, if you have any comments, questions, concerns, ideas, anything like that, let me know. This is just a cool application of color quantization that I thought of the other day. I'm pretty excited by it. Actually, I know I shouldn't be as excited about it as I am, but I am incredibly excited about this for some stupid reason, and I don't really fully understand why. So I got another notification from work. Let's say 30. Okay. 1 second. Okay. So 3.597, it is actually faster. So we're talking about not only 2.7% speed increase, we're talking about 2.8% speed increase. That's pretty good. Seems to be a nice way of reducing color depth. Yeah, that's exactly what it is. That's the color quantization. It's, I think, used for GIF, but I don't think it's used so much for JPEG. I think JPEG just does a discrete cosine transform. But yeah, it's used for various formats. That's probably garbage collection variation. Oh, probably. Yeah, you're probably correct. Yeah, we have a lot of garbage collection. I'm going to do something dumb here. We're going to do the poor man's version control. I'm going to CP source quantize into source quantize, and we're going to do backup bku.jl, and then we're going to do get checkout source quantize.jl. So we're bringing it back to the previous version. Then we're going to say image 2 just to run it again. It's going to be equal to Quiltify. Control D, Julia double dash project. Sorry about this, guys. Using revise, and now we're going to do using Quiltify. Let's just do it all in one line. Images, image view. All right. Get stash. I should have done get stash and get stash apply. I didn't. So, just deal with it. Besides, I thought maybe I'd want to have 2 different files available. I don't know. I don't know what I was thinking. If you want both side by side, exactly. That's kind of what I was thinking, but you're right. That's probably garbage collection variation. Yep. Okay, so we're gonna let this guy precompile, give it just a second, and then. Okay, and now we're gonna do image is gonna be equal to load the pride flag. I don't know why I chose the pride flag. That was probably not the best thing to choose, but whatever. Now we're gonna do img2 is gonna be equal to Quiltify. Now, as a reminder, the implementation that we just did, the implementation we just did is still shoddy. The reason it's shoddy is because every time we create the array of pixels to be held within each child, we actually just assume that the array of pixels is the size of the array of pixels of the parent. So this means that it's actually, we're using a lot more data than we need to, right? And we're using a lot more data for what is essentially, let's do using benchmark tools as well, a 2.7% speed improvement. And when I say a lot more data, we're using a lot more data. We are basically storing the image itself in each one of the child subnodes, such that at best, each level will hold an entirely new image. So image processing has never been quick. Right, I mean, again, we could try to GPUify it to make it a bit faster, but I just don't know if RAM is free. RAM is, okay, maybe in the CPU world. I'm very used to working on the GPU world, where RAM is most certainly not free. You have not very limited space, but you have limited space. 3.726. So again, last time it was 3.6. This is 3.726. I think we're going to keep the other version because it's more readable and stuff like that, and just say that, there could be ways to optimize it. Okay, so we spent basically the whole day trying to optimize this one function, and we've gotten nowhere. So let's move on to the next bit. I think in the next 30 minutes, we can kind of get this next bit done. 3.7, it's about the same. Okay, so let's go into quantize.jl. So this to-do has already been done. So we have a few more to-dos to do. So quantization may fail if there are no colors available for the box. And then also we need to take the endmost populated boxes. So again, what we're doing here is we're taking our image, we're moving into RGB space. And the idea is in RGB space, we take the image, we cut it down, up, down, left, right, forward, backwards. And And we basically try to figure out the minimum set of, or rather, we try to figure out where each pixel fits in this color space, right? And yeah, that's the idea. So we figure out where the pixels fit in that color space, which means some boxes could have a lot of colors, right? If you have a really, really red image, then there's a lot of red pixels. And so the red side of the RGB graph will be particularly used, whereas the blue side might not be, for example. So we want to find a way to pick the n most populated boxes instead of just n boxes right now, which is what we're doing. So what is a quilt? A quilt is... A lot of people ask this question, and I find it kind of surprising. I mean, I feel like everyone knows what a quilt is, right? So let's just do Mirage quilt.jpg, JPEG. This is a quilt. It's a thing you sew up. Like, I mean, you know. By the way, hey Crophead, how are you? We are basically taking an image and turning it into one of these. That's the idea. So the first step is color quantization, and then we have to do like basically quilt pixelizing that. So we have color quantization halfway working. We're working on making it faster and more optimal and all that kind of stuff. Not native. Oh, totally fair as well. Like absolutely totally fair. I'm sorry. I didn't mean to sound like I'm being a bit. I didn't mean to make fun. I'm sorry. I apologize for that. It's just we have the question a lot. And it is weird to me because I thought quilts were very common, but maybe they're not as common as I thought. Also, again, when you translate it to another language, surely it's different. Okay, so let's go into source quantize.jl, and let's try to find those n most populated boxes. So for now, what we're doing, in order to find our set of boxes, is we are finding our color set here. Okay, so how does this work? We are basically saying, we're basically doing a breadth first search over all of the boxes that we have. I'm considering watching the presidential debate. I am also considering watching the presidential debate. For those of you guys who may be in the United States of America and are thinking about voting this year, I would consider voting this year if you could. And yeah, that's basically it. It's kind of, I just don't, I don't know. Politics is weird, man. Like politics is weird. Go vote. Yeah, definitely go vote if you can. Okay. And it's easier than ever, what with all the absentee ballots and stuff that you can use. But it's 3 a.m. so I probably shouldn't. I just realized, yeah, so for people in Europe, it's probably quite late, or quite early, rather. Okay, so what are we doing right now? Right now, to find the color set, we're literally doing a breadth first search over all of the boxes in our image and just taking the first 8 boxes that appear. So we need to think of a way in order to find the 8 most populated boxes. So I think a good first step is doing a breadth first search. So what we probably want to do is we probably want to, at every step, we want to find the, so we go box, right? And we said this has, let's say this has 20 particles in it, this has 10, this has 5, and this has 7, or something like that. I don't know. It's just some number of pixels are in each box, okay? We go through, and we need to find some way of sorting a graph is the problem here. And the way I'm storing my graph right now does not lend itself very well to sorting in this way. Yeah, it doesn't lend itself very well. Why do we need the most colored boxes? Because the boxes with the highest number of pixels in it will correspond to the most used colors, if that makes sense. So for example, if you have an image that is really, really, really red, then you're going to have a lot of particles up here in this corner here. And so if you have a lot of particles or a lot of colors up here in that corner, you probably want more red representation in your color quantization, right? So the question is, how do we pick the n most populated boxes when the boxes are on a graph? Yeah, the boxes are in color space. A lot of people get confused about this, and I didn't do a good job of explaining that. But again, we're taking an XY image, we're moving it into a more Cartesian-based color space, and we're dealing with it there. So it's not like we're just taking the upper left-hand corner or something. We're taking the colors that correspond to the most red or the most blue or the most green or something like that. Okay. So what we can do, we're already putting all of the nodes into a queue. How large are the boxes? So because we're in RGB space, this is always going to go from 0 to 1, and the boxes are always split in half. So 0 to 0.5, for example, 5. So this will be 0 0.5, 0 0.75, 0 0.875, I think, and then 1. Yeah, that looks right. So that's the idea. It's always split in half. And then we just do an average of all of the colors inside of it to say the color of this entire box is the color of all of the pixels averaged on the inside of it. So that's how we do it. Okay. So again, I feel like if we had stored, how do you decide where to split? You just split in half every time. And some boxes don't have any pixels inside of them. So you split. Some boxes don't have anything inside of them. That could happen. So basically, you keep splitting until either you've hit some level depth. So we could say that we split 1, 2, 3, 4, and we say we only want 2 levels, so we only split once. Or we want 3 levels, so we split again, right? So we do 3 levels, or you keep splitting until every box has exactly 1 color. So we split to a level depth, or we split until every box has 1 color. So those are the 2 ways we do it. Yep. Either way will work. I have it implemented to split to a level depth right now, but that is actually something that we should put on the to-dos up here at the top. So another to-do here would be split until every particle. In fact, that's actually an easy thing to do. Let's go ahead and fix that right now. So we're going to do divide octree, and in here we basically say we're creating new extents for each child box. We say if the level is greater than max level, we return, but we need something else in that if statement. If box.n, if box.n is less than or equal to 1. So if the so now I need an or statement. Box.n is less than or equal to. Why does that look weird? Less than or equal to 1. Am I dumb? How do you less than or equal then? Crap! It must be this way. What? Why don't I remember how to do... What? Chotomate. Julia? That's true. Okay. Less than or equal to? What is less than or equal to? What is less than or equal to? Less than or equal to. Julia. Why am I not able to remember this? That's greater than or equal to. But I just tried that one. What? I swear I just tried that one. Didn't I just try that one? And it didn't work? I'm super confused. I did 1 less than or equal to 2. Okay, Julia must have just failed on me. Okay, fair enough. I had it right. I'm just dumb. Let me see. If 2 pixels are identical, they will always be the same box, no matter how small it is. Yeah, that's true. If you have a max depth, then why octree? Can't you just make a grid? Why octree? Can't you just make a grid? Because you need to... It's a way of clustering. So octree is a way of clustering. Holy crap, are you the guy that did... I did do an FFT video on YouTube. That is honestly my least favorite video I've made. I have made on YouTube, and I need to do a lot better. That is... I'm glad it was helpful, but also, like, I need to do better. I'm currently in the process of revising the FFT stuff on the algorithm archive. So just to reduce memory. It's not only just to reduce memory, right? Like, for example, again, we're looking for the n most populated boxes. So this box here, we will treat as one giant box, right? So thanks a lot. Yeah, I appreciate that it was helpful. Like, I appreciate you saying that. So, like, this basically means that any pixel that falls within this box, or any subset of these boxes, will be cast onto the average pixel value for this box, right? So, like, for example, if this is, I don't know, this color red, it also encompasses, a couple pink values inside of it as well, but we're just casting all the pink values onto the red value, right? So To me, I'm not really sure how I would represent that on a grid, because it makes more sense to represent on a graph or a tree, where I say the tree has like 4 or 5 children, and then we go from there. Each box has 1 pixel, or is it as small as possible? No. So it will have like, so this box will have 20 pixels, right? So so this box will have 20 pixels, and then it will have 4 sub boxes, one with like 5, 5, 10, and then 0. And then this guy will be split up into 3, 2, let's do 1, 0. And then this one will be split up, similarly, in this, and then this one won't be split up at all, right? And so the idea is, eventually, you get to where you have exactly 1 particle in each box, but it might take a while, right? So it might be very far down the tree that you do that. And so at every point, like, you're going to be averaging. So this is going to be some average value of these guys. This is going to be an average value of these guys. And this is going to be an average value of all of these guys. And so to quantize the colors, you just say, okay, well, we're just going to treat all the 20 pixels that fit in this box as a single value and not worry about it, right? So you want the most popular groups where the groups can be any size, right? So this is also how you do video codecs with space partitioning and image compression. Yeah, so some forms of image compression are done this way. Not all forms of image compression, right? It is somehow very surprisingly similar to JPEG, but for some reason, again, we looked at this just yesterday, and it looked like JPEG just does a DCT, which is like remarkably different than what this does. So it might be DCT plus color quantization, but I will say that GIF and the graphics interchange format file and stuff like that will definitely use some form of color quantization. So I'm looking for the 20 largest. Do you mean the 20 largest that still cover all the colors, but overlap as little as possible? See, that's a good question. So the issue I'm currently having, so what I did is the following. JPEG, yeah, that's what I thought as well. I didn't think that JPEG did color quantization, but it does something similar. Again, I thought it was just discrete cosine, but I could be completely wrong about that. So what I'm doing right now is I'm doing a depth first search over all of the nodes. Yeah, discrete cosine. Yep. Okay, good. So we're on the same wavelength then, CropEp. So what I'm doing right now is I'm just doing a depth first search over all of the nodes. So here's all of our nodes. I'm sorry, breadth first search. Breadth first search over all of the nodes. And then I'm just saying, I think you're right. So you're bringing up a good point, CropEb. I do appreciate the conversation. Definitely do, as always. The question is, do we want to have the biggest span of colors, which is what I'm currently doing with breadth first search. So like this is going to be red, this is going to be blue, and these are going to be somewhere in between red and blue. And so here we're kind of spanning through it. And if there happen to be no blue colors, we're skipping that node, and then we're doing breadth first search again. But the issue there is that we start over here on this side. So like, maybe we should switch the queue to a priority queue. And I think maybe that will solve all of our issues, right? So my question is, what happens if, for example, we just have no particles down here in the corner, right? So if we have no particles in the corner, then we're not really going to do we're going to have to go deeper into one of these guys, right? So right now I'm just going deeper into any of these at random. But in principle, I should be going deeper into this one because there's more particles in that one. So if we do a priority queue, it should be good enough. That way we're getting the span of all the colors as best we can. But then if, for example, we can't span all the colors, then we go one level deeper looking for another set of colors. Linux _ nice emotes there. Yeah, so let's see if we can do priority queue appropriately in Julia, and then that'll be my solution for now. Priority queue, Julia. Priority queue, is it the same as regular queue? Probably. So let's just try changing our queue here to a priority queue and see if that works. I'm a big fan of priority queues, by the way. I don't know if I've said that before, but we use them so much, it's just insane. So let's do using revise, and now we're gonna do using Quiltify images image view. Good to see the lack of colors in your terminal. Yeah. So it has been. Let's see. I feel like I should still make more emotes. I have a few emotes that I can still make, but the problem is the emotes that I can still make are for those that are like for tier 2 and tier 3 subscribers. And I kind of don't want to support tier 2 and tier, like, don't get me wrong. If you want to support me at tier 2 or tier 3, I appreciate that. But also, I don't want to, like, act like I'm begging for that. You know what I mean? So, okay, so let's try doing image here, loading the pride flag. And then after that, we're going to do image 2. So this should just work, I think. Oh, no, it does not just work. No method matching data structures, priority queue, Quiltify, we're 0. Okay, so we're not using priority queue correctly. That's fine. Okay, so construct a new priority queue with keys of type K and priorities of type V, forward ordering by default. Let's just mess around with this priority queue and see if we can figure it out. So priority queue here, and then we say PQ. Oh, this doesn't scroll. That's all we have for priority queues. So we say priority queue of A is equal to 10. Priority queue of B is equal to 5. Priority queue of C is equal to... Let's just mess around with it. See what we can do. So we're going to do PQ is going to be equal to priority... Am I misspelling it? I guess data structures. Using data structures. Okay, now let's try PQ. Is going to be equal to priority queue here. So we've created a priority queue. Wait, did you? Oh, the pop. Huh? No replace. Yeah. So let's see what we can do. I should be able to pop something. So I should be able to PQ. How are we doing it right now? So here's our queue. Here's our NQ. So can we NQ onto PQ? So NQ onto PQ, and let's just put a 1 or something. Int64 has no field first. Maybe I should have defined... So it's a priority queue, and we're just going to say of int64. And then we're going to say that. No method matching priority queue, int64v not. I gotcha. Okay. So the issue here is that we need int64, and then we need some sort of lambda function, I suppose. See, Alex, or gotta go. Interested to see what the final speed is when I watch the VOD. It's probably not going to change too much. We're on something else now. Replacing the value is twice as fast as removing and adding together. So most languages also provide a replace method. Interesting. So Julie is new, so it hasn't done that yet, I guess. So what I need to do is figure out how... So what is V in this case? So V is going to be... I think you need to teach it how to compare boxes. Exactly. That is exactly what I think V is. So V is the... priorities of type V. So do I then need to just give it a function which just says, okay, A is equal to 10, data structure is priority queue. Can I do the following? Let me just try doing a priority queue. And then we're going to say PQ, NQ on PQ. And let's try enqueuing A, 1. All right, now we're going to try enqueuing B, 0. Okay, fair enough. That's, I guess, what I would expect. So now we want maybe if we just do, you can use it as a map. What I'm going to try to do is the following. Exactly, that I find that weird as well. DT here. So we're going to do priority queue there, and when we do the NQing, so if we do DQ of PQ, we should get DQ exclamation mark. Okay, we get B. That's what I expected. So can we do? So let's do NQ, and I'm going to try NQing something else, which we're just going to say is an array of 1. Okay, this works just fine. It's dumb, it works just fine. So temp is equal to D, so we're going to NQQ box, and then we're going to try box.n, and then we're just going to do that for all these guys down here. DQQ, and NQ child, and then child.n. Now, I believe, yeah, so this is after the tree creation. So I should be able to do image2 now is equal to Quiltify Quantize, and let's just see if it works. And see if it's significantly slower with the priority queue. Nothing has no field N. Nothing has no field N. This is because some of the children are nothing. Why are some of the children nothing? 1 second. So we have quantize line 89. But the children shouldn't... So we have the color as a union. So it's going to always force you to choose the highest level box, right? This is what I'm trying to do, yeah. Since it contains all the pixels, no colors, no box. No, the box should still be created, even if... The box should still be created, because here we defined all the children. So in the dividing of the octree, we say the color box has nothing for the color, but then it has 0 as n. So we've defined it as nothing, and then the set of children that it could potentially have. Again, this isn't the best notation. We're kind of winging it a bit. And then we have 0 and 0 again. So let's see. We have make octree in here. So for finding the color set, we read in... so we do read in the box, which is the... So this is after the octree has been made. Is it a max Q or min Q? It is a... It looks like it's a max... Oh, this is a min Q. You're right. So we want to make this a... We want to make this a... You're right. We want to make this a... max queue. So construct a new priority queue with given type, ordering base ord forward. Let's try forward. I'm not sure which one we want. So we'll do priority queue, and then ord is equal to this. No, that didn't work. Maybe I need to do this. How is it? I just saw the KV. Oh, so it should just be order. So if we do this, that should work. Okay, so now we're going to say NQ that, NQ 3, sure. Oh, 1, 2. Okay, so we want reverse ordering. Try it again. Yeah, we want reverse ordering. So here we're just going to do base.order reverse. And then in principle, let's just see what happens. Write that. Go over here and we're going to go to, try it again. Nothing has no field n. Did I write it? Okay, so this is on line 89. So I was checking a 0 box, I guess. Yeah, so that I was on the same wavelength as you were. But it doesn't seem to 89. So it's on this NQ of box and then box.n. On NQ, why would it be an issue with NQ? Log the boxes? What do you mean log? Let me just do print line type of box. Write this, go over here, and then we're going to try it again. Try it again. Revise.retry. Okay, right. Okay, Control D, double dash project using revise. Try it again using Quiltify images image view. Am I still missing one? No way, I'm still missing one. Oh, I think I am. You're right, I'm sorry. I'm dumb. That's okay. Yep, I hear you. There we go. This one should work. Okay, then we're going to try it again. Let's see. Wait, what? How, though? How am I this bad? Where's the extra... Where is it? You're right. Okay. So what's this one? This is on line 89. That's line 89. Try it again. Sorry about that. Okay, let's see. I think every time Simulator says he's dumb, he should have to put $1 in a jar, and then when the jar is full, he takes his lovely better half out for a nice dinner. I have not seen her in almost a year now. It will be a year until I see her again. So I'm not going to be able to spend. Also, like by the time I see her again, there's absolutely no way I'm going to be able to spend, what is probably going to be $1 million on a single dinner. So let's do image equals this. And now let's try this again. So image 2 is going to be equal to Quiltify. And it says it is a type nothing. How is it a type nothing? So we're going deeper down. Okay. So let's see. Type nothing. So find color set. Why is it? We are. What? I don't understand what's going on here. We do make octree, and then we do the color set is equal to just a random set, and then it doesn't immediately fail. No, it fails on. Wait, I'm confused. We shouldn't. Okay, so we made the octree, but the find color set function shouldn't even be called. Wait, where are we? We are on line 119. Yeah, it's on this. So if I comment that out, it should just work. Because we're not calling the function anymore, so it should be fine. Okay, that worked. So that's fine, I guess. It just wasn't outputting what I expected it to output. Okay. So then we have priority queue based order reverse. I think that's what we need. And then we enqueue. What is a quilt? Again, get this question a lot. It is this. It's something you sew together. It's a blanket you wear on cold nights. That's a quilt. We're making a package. Is octree broken? I don't think so. Because no, we're able to make the octree just fine. Let's see. And again, so I guess we can take a look at the octree though. So image, we'll say tree is going to be equal to make octree. Quiltify. Dot make octree, and then we're going to take in the image, and we're going to take in 2 levels. Okay, so now if we do tree, we should get tree dot type of tree. Okay. I don't understand what happened. Make octree, divide octree. This was working a second ago, so get diff of source quantize .jl. Find color set. If max level or box. Okay, no, I see exactly what happened. This is in that statement there. So we're looking at divide octree. It's I screwed up when I defined the original box. I defined the original box to have 0 particles in it, which is clearly wrong. It should have, let's see, make octree in here. So the number of particles in it should be length of image. Write that, go over here, and now it should work just fine. Yep, now it's working just fine. What language were you using, Julia, for this? Okay, so now let's try IM show of img2, and hopefully it looks nice. It should be, we should know what this looks like because we've seen it multiple times before. Yeah, that looks right. Good. So I'm happy enough with that. So let's do git add source quantize .jl, git commit -m, adding priority queue. All right, git push origin development. All right. So I think that's an okay place to stop for today. So let's go ahead and see who's live on Twitch and who we want to raid at the end of stream. We've got Master Mindo. I think we just raided him yesterday. We've got L. Swigart, who I think is the Python programming with the author of Automate the Boring Stuff. Usually people quite like his stuff. Let's see. We have Shell and 50K. If there's anybody that want to raid, let me know. Otherwise, I might do Al Swagart. That might be what I do. So let's go ahead and do that. Raid Al Swagart. Okay. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys around next time for the next episode of Simuleos when we do stuff. Hopefully some graph traversal stuff actually for lecture, and then hopefully some more Quiltify after that. We'll see how it goes. Thanks again, guys, and I'll see you next time. Bye, guys.